Welcome to the sixth video in Introduction to Quantum Field Theory. We will be talking about the preliminary topic, namely waves, because those are very important in quantum field theory. When a field is given an excitation, so for example, these fields right here, when a field is given an excitation, the resulting behavior is wave-like. So it's useful to study these waves. Mathematically, we know we are dealing with a wave phi. So phi is a wave, or maybe more accurately, we can say wave-like. Phi is wave-like if and only if it satisfies the wave equation. So the time derivative minus some parameter, which we're calling v, the derivative in the spatial direction. This is one-dimensional. This is the one-dimensional wave equation, but we can readily extend this to 3 dimensions, 4 dimensions. Like the math is essentially the same, so it's easiest to just show it in 1 dimension. So it is wave-like if and only if it satisfies this wave equation. So I'll label this right here. This is the wave equation. And specifically, we'll see what this means later, but it's without dispersion. This is the wave equation without dispersion. Note that this V right here, this is an element of R and is the magnitude of the wave's velocity. It ensures the derivative operator has the correct units. The constant v ensures that the derivative operator has correct units. These correct units are, so if we have dt, this has units of 1/2, and this constant v, which is, remember, velocity, and we have dx, as components. Velocity has meters over seconds, and dx is 1/meters, which is equal to 1/seconds. So you can see that these do have the same units. And that's what this constant of velocity does. So solutions to the wave equation usually look like the following. So they usually look like this. Phi as a function of time and space is equal to E, where E is Euler's number, E omega t minus kx, where omega, do a better omega, omega is angular frequency, and k, which is defined as 2 pi over lambda, is the wave number corresponding to a wavelength lambda. Okay, so if you have a wave, well, if you have some wave, this is not a great wave, then this distance right here is the wavelength, and the number of these in time. So if in so if you have, say, the number of these passing a certain point in time gives you the angular frequency. And so there's a relationship between angular frequency and this wave number right here, or and wavelength. But there are also different solutions that can work. So solutions like phi dx equal to cosine omega t minus kx, or phi tx equal to sine omega t minus kx. So solutions like this work equally well. And this is because of the Euler formula. And the Euler formula is e to the I theta equals cosine theta plus I sine theta. So in general, this is the most general solution. This is the most general solution that is not a sum of other solutions. And the reason it works is because it's just a sum of cosine and sine. These are called plane wave solutions. These are called plane wave solutions because they describe a wave-like function spread all over space and with a constant amplitude. So, an example of this, let's just create these and have space like this. Then if you have some function that, oop, that's not really bad at drawing. So it goes like this, and then it continues on throughout all of space. So you have this thing kind of going throughout all of space. This is space. This is the value of the wave. Then this is called a plane wave. Now let's look a little bit at the relationship between this omega and this k, so the angular frequency and the wave number. So we can look at the relationship between them. So looking at omega, omega and k. If we plug in this right here into the wave equation, then we can determine relationships between omega and k. So the first thing we do is to distribute the wave and then take a derivative on both of these. So the derivative of this with respect to time is only going to have a factor of I times omega come to the front. So you're going to have a factor I omega dt e I omega t minus k x. And then similarly, you can have I minus k come out to the front. So minus v squared minus k I minus I k. Then another spatial derivative of I omega t minus kx. And we can take the derivative one more time. So we get I omega squared. Then we end up with e to the I omega t minus kx. Then minus v squared minus I k squared. E to the I omega t minus kx. We get this, which, all right, let me put this in the middle. It's not a very good put in the middle, but whatever. This is equal to 0 if and only if, so we can imagine simplifying this. If this is equal to 0, we can divide by this common factor, and then we just have minus omega squared, and then plus v squared k squared. So, which is, we end up with omega squared is equal to v squared k squared, which implies omega equals vk. So this is the dispersion relation, and it shows us that if this wave function satisfies the wave equation, which is done by saying it's equal to 0, then you get this relationship between angular frequency and wave number. So for relativity, or rather in relativity, there exists a unique relevant constant with units meters over seconds, and that is c, which is light speed. So we get this in relativity, we get this result, relativistic quantum mechanics, that is. We get the result that c is equal to omega over k. Which is plugging in c into this v and then dividing by k. This actually turns out to be for massless particles. So what happens if we consider massive particles? So for wave equations describing objects or describing massive particles, the wave equation with what's called dispersion is used. Let me just go back up here. Yeah, okay. So this was without dispersion. So it turns out without dispersion means that you're dealing with massless particles. And the wave equation with dispersion describes massive particles. And what this looks like is dt squared minus c squared dx squared plus some constant mu squared phi equal to 0, where mu is a constant proportional to mass. It's not exactly equal to mass, and the importance of that is not going to be covered in this video, but it's proportional to mass, so it does describe mass. We can find a dispersion relationship just like this. So I can say, looking at omega and k, so omega, k, and mu, omega, k, and mu, then we end up with dt squared phi minus v, or now we know it's c squared dx squared phi, then plus mu squared phi. Then if you want, you can go ahead and expand this out. That it's the exact same expansion as this, and we know that it ends up being equal to, or corresponding to this, or being equal to this specifically. So I'm just going to directly jump to this. But I recommend that you actually do this by hand so you can get used to working through working through the math here and understanding it. So it ends up being negative omega squared phi plus c squared k squared phi plus mu squared phi, which is which is equal to 0 if and only if omega squared is equal to c squared k squared plus mu squared. So now there's an extra term. And in the result that this is massless, then mu is equal to 0, and that reduces to the massless case. Massless case. So this for massive particles. Though technically it does describe massless particles as well. This is the generalization. It just mass equals 0. So there is a quantity. There's an important quantity here. There exists a quantity called phase velocity, which is defined as the phase is equal to omega over k, which looks familiar, and it should. It's what we have up. It's what we have up here. And indeed, in the massless case, you have that mu equals 0, which implies that omega is equal to ck, which implies that the phase velocity equals c, which means that the particles are traveling at light speed. Then if you have massive particles, your mu is not equal to 0, which implies that omega is equal to the square root of c squared k squared plus mu squared, which implies that your phase velocity is equal to c squared k squared plus mu squared over k. And it turns out that this means that fa this phase velocity for massive particles is always less than c, which means that particles that have mass must travel less than the speed of light. So we can see that these wave mechanics can obey special relativity. There's also another important concept called wave packets. Wave packets. are important. And we have two cases. We have, or I'll just do this. Wave packets are important. You have a massless case, and you have a massive case. Now, the first one is, say I have some wave like this. Oh man, I'm not good at drawing. It's like this. This can be your initial time, which then goes to this, which is your second time, goes to this. And okay, I'm really not good at drawing. Goes to this at T2. So you can see that there's a little bump here and it travels along and the bump stays together. This is called a wave packet. And we actually saw what wave packets were in these things. It's basically if I pull up a certain spring from equilibrium and then I let it drop, then you're going to have some waves propagate outward. And the waves that are propagating outward are called wave packets. So this is a wave packet. This is for massless particles. And for massive particles, you end up with, so if we start with the exact same, we start with the exact same wave, then we end up with something that looks a little more spread out. So it's still moving. It still has moved. The center of it has moved to the right, but it's a little more spread out. And then it's, okay, it's like this, T2. So the center has been moving to the right, but it has dispersed. It's not as localized. This is what happens for massive particles, and it's a result of the wave equation having a mass term. The reason this happens is actually because at for massless particles, all the phase velocities of the waves that make up this packet, all of the so each individual wave that makes up a wave packet here travels at c, so they don't disperse. But for massive particles, you're going to have wave numbers that are different, but you'll have the same mass, which means you're going to have different phase velocities. So you'll have some phase velocities that are going faster than the average, and then some that are going slower than the average. So some that are going faster, so you'll have things go out here, some that are slower and they'll go out here. So it disperses, but the average will be the same. So I'm sure you're wondering what wave packets are mathematically. So mathematically, wave packets are superposition. Okay, superpositions of plane waves. Technically, they are superpositions of plane waves that are localized to a finite region. We'll talk about that in a sec. So, how does this work? Well, suppose that the wave equation is satisfied for one for one wave, and it's satisfied for some other wave, phi 2. Well, if this is the case, then the sum also satisfies the wave equation, which makes sense. If I plug in phi total equals phi 1 plus phi 2, I just get these two things which are equal to 0 individually. So this whole thing must be equal to 0. So that would prove that it's also a solution to the wave equation. So a wave packet, so a wave packet is a sum of plane waves such that the field excitation, the field excitation is localized within a finite region. So an example of that is you have a wave packet. It's defined as the sum of different waves, which can be thought of as having amplitudes, and then the actual wave component, which can have, or I'm just going to write k mu, and they're going to be such that, or the sum of plane waves is a wave packet if and only if it represents a a field excitation that is localized within a finite region. And it is here. It's this little bump. And you know that the bump isn't anywhere else. It's not located, it's not infinitely wide or anything. It's within a finite region. So this is a wave packet. And this k mu is equal to the jth mass squared, which is just omega j squared minus c squared k j squared. So this is just the stuff that we've been talking about before, but instead, instead just using whatchamacallit, using different, we have different waves. So having having lots of plane waves gives a more precise wave packet. So if we have position space, and if we have wave number wave number space. Have that here, have that here. Then supposing that this is representing space, and this is representing wave numbers, all possible wave numbers. Then if I have a super localized wave, then these are equivalent to having lots of different k's, which means that the k's on this end will end up canceling with the k's on this end, and so they give a very precise location. But say I don't have a precise location and I'm not localized, so that means it's pretty close to just being a plane wave, then I effectively just have one wave number. And so as position space gets more precise, more localized, wave number space goes up. As position space becomes less precise, wave number space becomes more precise. And this is actually Heisenberg's uncertainty principle, which is actually a result of wave mechanics, not quantum mechanics. It's just because quantum mechanics are waves that it has this property. But this is something that actually is not fundamentally quantum. And wave numbers are related to momentum, or momenta, so that's where you get the Heisenberg uncertainty relations because position is conjugate to momenta, and momenta is related to wave numbers.